Hastings.
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 Hastings. Hi everyone, we're going to start the talk of Larry Hastings about all dancing, all singing, Python bytecode. Please turn off your cell phones and enjoy.
Okay, I do have an hour, but people were still shocked at how fast I went. So I'm going to go really fast because I have a lot of material to cover. Maybe we'll have time for questions, or maybe you can just talk to me in the question and answer in the halls afterwards. So this is an intermediate level Python talk. The talk is all about Python, specifically CPython. I say CPython to differentiate the different implementations of Python. So like IronPython is written in C# and Jython is written in Java. CPython is the version of Python written in C, but it's the version of Python you get when you just type Python in at your prompt, and it's probably the version of Python you're using. Now, it probably actually isn't the version of Python you're using because I'm giving the talk in Python 3.3. Because I'm a Python core developer and 2.7 is in my rearview mirror. But the talk will be 100% in Python. There will be no C anywhere in the slides. And while the information is specific about CPython 3.3, it's roughly applicable to some other places. Previous versions of Python 3, it'll still be true. It's even really still true about 2.7. It's even kind of true about PyPy. The PyPy bytecode is very similar to CPython bytecode. However, IronPython and Jython, the bytecode itself is very dissimilar looking because the whole point of those is to use the native bytecode of their JVM or CLR runtime. However, the concepts involved will generally be true. And I think even some of the things, some of the slides that I'll show you may even work on some of those systems. Now, what is bytecode? Very simply, bytecode is an instruction set for a virtual machine. Now it seems like every time I give a talk I give the same metaphor, but a virtual machine is one of those really apt metaphors in computer science in that it is both virtual and a machine. It is virtual in the sense that it's not a solid piece of object of matter that you could go over and kick when it misbehaves. And it's a machine in that it has all the attributes of machine. And when we say machine here, we really mean computer. So it has registers, it has a stack, it has memory, and it has an instruction set. And that instruction set we call bytecode when we're talking about a virtual machine. In general, because the individual instructions are 1 byte long. That's what most people do. Now, I would break CPython bytecode into roughly 4 categories. These are very rough, unfortunately. They're stack manipulation opcodes, like load and store. These allow you to manipulate the stack. They're flow control operands like jump. These allow you to manipulate the instruction pointer. There are arithmetic operations. These allow you to perform math like plus and minus and times and divide and shift. And then there's this grab-all bag of Pythonic bytecodes which do things that are specific to the Python interpreter, like creating a tuple or creating a set or loading a closure. And there are some things that just exist as dirty little details to make the interpreter's life easier. Now, when does the CPython use bytecode? The answer is all the time. Anytime that you're running Python code in the Python interpreter, you're actually running bytecode. Which means actually that any program that you can express in Python code, you can express in bytecode. The reverse, however, is not true. There are programs that you can express in bytecode that you cannot express in Python code. Like, for instance, you can jump arbitrarily any distance you want in the interpreter with bytecode. You don't have a goto instruction in Python, and I think that's probably for the best. Now, why have bytecode at all? The answer here is really simple. This just helps you to manage the complexity when you're writing an interpreter. This is a very standard paradigm for writing an interpreter. Everybody uses it. Ruby uses it. PHP uses it, although its bytecode is crazy. Every interpreter for Python has some form of bytecode or another. Now, it may be a little late. We're 5 minutes in, and now I'm asking the question, why bother to look at it at all? I was hoping you might have an answer for me, since you're sitting here and trying to learn about bytecode. But I think there's only one good answer if you want to learn bytecode. The reason you might want to learn bytecode is because it's an inherent part of the CPython interpreter, and if you want to hack on CPython, obviously you need to understand how it works. You need to understand bytecode. So that totally makes sense. There's some other reasons that people cite that I thought about, and I don't think they really make that much sense. So like people say, you need to really understand what's going on. In order to understand Python, you really need to understand bytecode. And I guess that's kind of true. It's sort of intellectually satisfying, but the problem is, where do you stop? In order to understand bytecode, in order to understand Python, you have to understand bytecode, but to understand bytecode, you need to understand C. And to really understand C, you should understand assembler. And to really understand assembler, you need to understand processor microcode. And to understand microcode, you need to understand digital logic. And underneath that is transistors. And underneath that is physics and electricity. And underneath that is special relativity and quantum mechanics. And I can guarantee you, ladies and gentlemen, that you can be a productive Python programmer for a long time and never understand quantum mechanics. Now, some people like to write hand-tuned bytecode. And to them I say, well, okay. Hand-tuned bytecode means you write a little assembler and you write your own functions and you skip the whole Python step. And you can squeeze out a couple of extra cycles this way. But it's theoretically fragile, although again in practice bytecode doesn't really change that much from one version to another. It's just that I think that you're kind of spending your time in the wrong place. You're probably better off making your algorithms a little bit better. Finally, this is the most likely reason, if you're not going to be a core developer, to understand a bytecode. And this is that the bytecode is the granularity at which the GIL happens and at which threading happens. So a single statement like A equals B even, that looks like a single atomic thing in Python, but it's actually two bytecode statements. And something as complicated like a function call with parameters that have expressions or subfunctions, that can be many, many, many bytecode instructions. And the thread could switch, the GIL could jump between threads at any point between any of those two bytecode instructions. So to really understand Python threading, it's probably helpful to understand bytecode. Now, in order to talk about bytecode, I kind of need an example program. So this is my example function in Python. This is called gunk. It doesn't do anything useful. It's really pretty pointless. It just demonstrates a bunch of things about bytecode that I want to go over. So let me draw your attention to a few things about it. We have one argument called A. It's positioned over a keyword. It has a default of 1. And then we have a star args. That's going to be all the remaining positional arguments stuck into a list. Then we have a keyword-only argument named B with a default of 3. In the body of the function, we print out args. We create a local variable called C. We assign it a default value or an initial value of none. And then we return this stupid little tuple that contains A added to B, and then we print out and we add C to the end. Now, there is a built-in disassembler that comes with Python. It has for a long time. It's called dis, and dis.dis will print out the function bytecode for you. So here is all the bytecode for dis, all fit on the screen. So I'll walk you through what all these columns mean. This first column is the line number offset. So the first 4 operations, the first 4 bytecodes were generated from the first line, line number 2. And that line number is in the file rather than in the relative to the top of the, or maybe it is relevant to the top of the function, I can't remember. Anyway, the second column, that's the bytecode offset. So the first bytecode is obviously at 0, that's load global. The second one is at 3. Now you may be wondering, I thought you said, Larry, that bytecodes were 1 byte, and this one is an offset of 3. What's going on is that bytecodes may or may not have an optional argument. Right now I want to establish this very early on. I'm going to call the bytecode the op, and this possible argument that it would have is called the op-arg. This is the terminology used inside the Python interpreter a lot of places, and so I just try and stick with it. So some opcodes have an op-arg, some of them don't. I'll show you how to tell the difference in a minute. But the first one does take an op-arg, and when there is an op-arg, it's the next 2 bytes in the bytecode stream. What you do is you take those 2 bytes in the bytecode stream. This one is the bottom 8 bits, this one is the top 8 bits. So you shift it left by 8, and then you OR them together, and that gives you a 16-bit unsigned number, 0 to 665,000, that one. So this third column, obviously, that's which bytecode you're talking about, and these have been shown you symbolically. They're actually just integers. And then this column is showing you the op-arg if there is one. So the op-arg is 2 or 0 or 1 or 3 or whatever it is. This column is a hint that this is showing you, saying, well, this is kind of what the op-arg represents. So load global is loading the global name print, but the actual opcode is load global 0. And load fast 2 is loading args. We'll go over what all of this stuff means in a minute. But what I wanted to bring your attention is what I find dissatisfying about this. I will remind you that A was position or keyword, and it had a default of 1. Args is this var args array, and it's always a list. B was a keyword only, and it had a default of 3. And C was a local variable. You can't tell the difference between these things. There's nothing on the screen that shows you that args contains this var args list, or that C was a local variable and A and B were parameters. So there's a lot that this isn't showing you. And in general, there's a whole lot that this actually isn't showing you. It's only showing you the bytecode, really, and just a little bit of extra information. Which is why when I was writing this talk, I realized that I really had to give you the whole picture. So the description of the talk is actually a little inaccurate in that I'm actually going to sort of do this holistic approach to bytecode. I need to show you not only the bytecodes themselves, but I need to show you the runtime environment that they run in, aka the Python VM, just at a very high level, just a couple of things about that. But I also need to show you all of the associated data and metadata that exist with the bytecode, because bytecode doesn't run in isolation. Consider a C program, a modern C program. A C program isn't just the instructions, the assembly language that make it up. You also have all the static data. You have the static integer that you initialize to 0, or you have the strings. A modern program that runs on a windowing system, that's going to have all sorts of things embedded in the program. It'll have dialog boxes and pointers and bitmaps and icons. All of that stuff is relevant, and you can't understand the assembly language without understanding all of it. And so there's a lot of this associated data and metadata with a bytecode that you need to understand in order to understand everything, and I'm going to go over all of it. But we'll start with the bytecode. So there are 101 opcodes in CPython 3.3, and a bytecode program is I said list of bytes here. What I really meant was a byte string. Internally, it's actually stored as a byte string, but conceptually, you can just think of it as an iterable of bytes. Each byte literally is 8 bits. So an op is a single byte, 0 to 255. And the op arg, if it exists, you take the next 2 instructions, like I said, and you shift it, and you OR them together. How can you tell whether you have an op arg for a particular instruction or not? Well, there is a constant number. It may change between implementations, so you just always use a symbolic constant. It's called dis.have_argument. Its current value is 90. And what this means is, if the operand, if the op is 90 or greater, then it has an op arg. And if it is less than 90, then it doesn't. So in short, the size of the op is either 1 if it's less than 90, or 3 if it is 90 or greater. Now let's talk about the VM, the environment that all this stuff runs in. There are 3 things that you really need to care about when you're talking about the Python runtime as a Python programmer. There's the instruction pointer, which you can manipulate again through jump instructions. There's the stack, which you manipulate through load and store. And there's what I call the fast locals array, which you manipulate specifically through load fast and store fast. I'm going to show you the stack in a minute, but I just wanted to talk about fast locals. Fast locals is a list. It's literally a Python list, and it contains all the local variables and actually all of the parameters. Conceptually, parameters are really just local variables that are pre-initialized before the function is run with funny values that somebody else gave you. But they behave in every other way like a parameter. And to access them, you call load fast and store fast to pull them in, push them onto the stack, or pull them off the stack and store them away. It's much faster than the other mechanisms. So let's talk about the stack real quick. In case you've never seen the stack, hopefully you have, because these are really bad diagrams. But all of the load instructions conceptually take something from somewhere off in memory somewhere, and they take a new reference to it and put that on the top of the stack. So amusingly, here's a diagram. Our Python stack can store any arbitrary Python object. So here we have a tuple containing arbitrary gunk, whatever it is. On top of that, we have a callable that represents the function print. We're going to push the number 3 on top of it. Wow, look at that. The symmetric operation is to store. What store does is it removes a reference from the top of the stack and stores it away in memory somewhere. And if it's overriding an existing object, then it decrements the reference count of that object that's being overwritten. So that would excitingly look like this. Pow. Slightly less uninteresting would be binary add. Binary add takes the top 2 things off of the stack, whoosh, and adds them together using dunder add or dunder r add, depending on whether they're playing nice today, and pushes the result back onto the stack. Bam, 29. So now I mentioned load fast. There are actually 6 different places that you can store and load memory from. and I'm going to go over each one of them. Global variables and built-ins are accessed through an instruction called load global, and you can also call store global. The oparg, I'll tell you for each one of these. All of these load instructions take an oparg, so you can know which one you're talking about. Load global is kind of indirect. The oparg is an index into an array, which I'll show you, of names called CO underscore names. And so what you do is you take the oparg, you index into that names array, which is an array of strings. And whatever that string is, that's the thing that you're going to load or store. So that's what load global 0 meant print, because print was the 0th string in the names array in my stupid little function gunk. Fast locals, as I mentioned, that's load fast and store fast, and the oparg is just an index into that load fast array. Locals, aka slow locals, this was the original mechanism for local variables in Python in the very early days. It wasn't long, it was a couple of months before Guido added the fast locals. But slow locals are just a dict that's attached to the function when it runs. And this is still the mechanisms that's used for class variables, for members, class members, for module level things, and for variables inside of an eval. And you load and store those using load name. And again, the index here is an index into the names array. Consts, you can load with load const, and there is just a table, it's actually a tuple, of constant values associated with the function called CO underscore consts. There is no store const, otherwise they wouldn't be very good consts. And to load and store object attributes, there's load attr. Again, the oparg is an index into the names array, so you know the name of the argument that you're going to load. And you have to push the object onto the stack before you call load attr. And finally, there's the really crazy one. To load and save cell variables, you use load dref and store dref. Now, what are cell variables? I'll show you in the next slide. I just want to mention for now that load dref once more uses the names array. Oparg is indexed into the names array. So what are cell variables? There are actually two things I got to talk about here, free variables and cell variables. Consider the function before you. We have a function called foo. Inside it we declare two variables, a and b. These are local variables. And then we declare a nested function bar with non-local b. This is everything we need. Now, a is a local variable. B is a local variable, but a specific kind of local variable called a cell variable. A cell variable is a local variable that is referred to in a nested function. And nested function could be a closure or could just be a normal nested function like this. Inside of bar, B is a free variable. Free variable is actually a term from compilers. It means a variable that's defined in some other basic block, something like that. In Python, specifically, a free variable is a variable that was defined in an outer enclosing function. There's some mechanisms involved in managing cell and free variables that honestly I don't understand, so I'm really not going to talk about them very much. You can go your entire life without ever understanding them unless you're writing a Python VM yourself. Anyway, I don't really have time for more information about that because I'm already running late probably. So finally we're going to crack open the gunk object, the gunk callable, and start examining the guts inside. First of all, gunk is of type function type in the types module, and it shows up, the repr is just class function. You don't even get to see the name. And if we look inside the gunk object, we see a whole bunch of stuff. The stuff that I made bold and large there is the stuff that's relevant specifically to function objects. But there's one in particular that's really interesting here. That's dunder code, right in the middle of the second line there. Dunder code is awfully important. That's the code object, which I'm going to break apart on this slide here. So type of gunk.dundercode, that is of type code type. It is of class code in the repr. And if we examine that, we see a whole bunch of stuff. Again, I made bold and large for your viewing pleasure. It all starts with CO underscore, and this is all the stuff that's relevant to code objects. So every function object points to a code object, and you need both of them in order to have a real callable that's implemented in Python. This gives direct rise to the question, why bother to have both of them at all? Why not, if we're going to have both function objects and code objects, why not just fold the code object into the function object and just have one object? Now the first thing I'll point out to you is that code objects are marshalable and function objects are not marshalable. Now what the hell does that mean? Marshal is a module in the Python standard library. It's kind of like Pickle. It's a binary serialization protocol, but you should never use it because it's awfully fragile. It's really only good for one thing, and that is it can serialize code objects. And it's used for .pyc files. So a PYC file literally, in Python 3.3, a PYC file literally looks like this. There are 12 bytes at the top, which are 3 4-byte integers. The first 4-byte integer is a magic value that says this was compiled by Python 3.3.0. The second 4 bytes is the date and timestamp of the .py file at the time that the PYC was compiled. And the third is the size of the file at the time it was compiled. And actually, by the way, that size field, that's a new one in Python 3.3. Previous versions of Python just had 8 bytes there. After those 12 bytes is a single serialized code object that represents the function that is the module. And so you need to be able to serialize code objects, but function objects contain live data that can't be serialized with Marshall, which I'll talk about in a minute. But it could be almost anything in there. So that's what I thought the reason of it was. Just as an example, here are some fields on the function object that contain references to objects that could theoretically not be Marshallable. So I thought that was the reason. I asked Guido about it, and he said, no, actually, that's not the reason. This distinction between the function object and the code object existed before you could even Marshall, before you could have PYC files. It's from very early in Python. And the reason is nested functions. Consider, on the previous slide, we had that foo with the bar inside. Every time that you run the function foo, it's going to create a new function object representing bar. And if it had to populate everything that was inside that, that'd be, well, kind of slow on a computer in 1993. So it's a lot faster to take all the stuff that doesn't change, that cannot change because it's immutable, and stick it in one object, called the code object. And all the stuff that does change lives in the other one, the function object, and we just create a new function object every time we rebind it. So it was a speed and size optimization from a long time ago. So back to cracking apart the code object. Code.co_code. This is what you've all been waiting for, ladies and gentlemen. This is the bytecode for gunk. Isn't that great? Isn't that readable? So that's the byte string, and that really is it. It's a little bit more readable or a little bit less unreadable in this form. I'll give you a couple of hints. Every number that is greater than 10 is an opcode, as it happens in this particular function. Every number that is less than 10 is part of a 2-byte oparg sequence. So 116 is load global, and then those 2 zeros, of course, those are going to combine together to be 0, so that's load global 0. The next one, 124, that's load fast. The first byte is the low order byte, so that's going to be load fast 2. Then we have call function, that's 131. The last one is return value. It's still not terribly readable in this format, but I'm going to show you the simplest possible assembler in Python. Now, I need to call into dist to get some values that I can't get anywhere else, but I can do it all on one screen, and here it is. I can't remember if I go over these. Do I have individual? Yes, I do. Okay. So our disassembler, first it prints def, then the name of the function, and the colon, so it looks all pretty. I pull out the bytecode from the code object inside of the callable. I have my instruction pointer, it's going to be 0. And until I hit the end of the program, I pull out the bytecode. If it's less than 90, then I don't have an oparg and I go forward by 1. Else, I pull out the oparg, assemble it properly, and I advance by 3. And then I look up the oparg in this dis module, this dis.op name that's a mapping integers to strings that are the symbolic bytecode names. And I print up the oparg following. I just do that in a loop. And if I run that on disassemble, I get this. So it's not terribly readable, but it's 80% of what dis is giving you, I assert. So load fast 0, load adder 0. Again, I'll point out everything takes an oparg except for pop top, binary add, and that's all that fit on the screen anyway. So I'll show you more useful disassembler in a little bit. Back to the code object. Now this is going to be a little bit of a slog. I think I have like 5 or 6 slides in a row that are just about fields in the function and code object. So strap in. It's going to be a heart-pounding ride. Just about the number of arguments. This is positional arguments. So gunk had 1 positional argument, and that was A. It had 1 keyword-only argument, and that was B. The total number of local variables is 4. So I'll remind you, all the arguments and all of the locals go into this. So And there's actually a matching list of their names called co_var names, so you can see what goes into it. A, B, args, and C. So the locals contains these things in this order. All keyword or positional arguments in the order they were declared, followed by all keyword-only arguments in the order they were declared, followed by the star args variable parameter, if you have one, followed by the star keyword arguments parameter, if you have one, followed by all local variables in the order they were declared. It gets reordered here from the way that you necessarily put it inside the thing because that's the order that Python overrides on it. Default values for the function are not actually bound until they can be calculated at runtime. You can have the default for a function be a tuple or a list or a dict or the result of a function call. So it can't be computed statically. So it's not part of the function. It's not part of the code object. It's part of the function object. So defaults is for positional parameters. And what you do here is this just has enough defaults for the ones that actually had defaults. So if, in example, you had a function that had 5 positional parameters and the last 3 of them had default values, then gunk.defaults would be a tuple of 3 things, and you just take and sort of shift it right to match the last positional parameter, and then you work your way backwards. A little bit simpler is kw defaults. This is a dict mapping keyword only parameters to their defaults. And again, it's on the function object. The tables that I've referred to a minute ago, so co_names, this is the one that all of those different opcodes referred into. Gunk only had one name. It only used load global, and that was print. This none that appears here is actually just leftover garbage from tokenizing. There is at no point will the Python interpreter actually refer to that co_names index 1. I asked and they were just like, yeah, it's just leftover stuff. It doesn't hurt anything. We never bothered to fix it, whatever. We're pretty lazy, I guess. co_const, this is another tuple, and this has the constant values that are accessed by load const. Again, gunk only had one, which was none, and so it's empty. Someone told me that every function always has a reference to none, even if you never refer to none inside of the function. It just always adds one. Line numbers. Python only uses line numbers when it's calculating tracebacks or when you're in the debugger. So this doesn't generally have to be a really performant thing. So Python has optimized very heavily for speed as opposed to size here. Excuse me, the opposite. I'm speaking very quickly. It's optimized for size, not speed. So it's a really inconvenient format. There are 2 things that are relevant. co_first line number, that's the first line number in the file where the function started. And then there is this really crazy LNO tab. Everybody hates this thing. So again, it's another byte string, and it's completely unreadable in this format. Slightly better is this way. The way that LNO tab works is it is pairs of bytes that represent the delta in the bytecode offset and the delta in the line number offset. And is that? Yeah, sorry. And there are some stringent rules on how you have to compute them. If you go over 255 in one leap, then you have to do something funny. On and on and on it goes. Like I said, it's a headache. Hopefully you'll never have to deal with it. Metadata associated with the function. So globals, this is a reference to the module dict where the function was defined. So that's how when you call a function and the function refers to a global variable, it can always find it because it carries around its reference to its globals dictionary wherever it goes. Gunk.module is just the name of the module. Co.filename, that's the name of the file where the function was defined. I typed gunk into the interactive prompt, so I got standard in. Co_name, that's the name of the function. Co_flags, this is a bit field. The number 71 is inscrutable, and you'll see it a lot. This is one of the least documented parts of functions and of bytecode. I'll go over what that means in a minute, but you're not going to be happy. And finally, co_stack size. This is the depth of the stack that will ever happen when this function is running. Python pre-calculates this in advance for 2 reasons. 1, it allows you to predict in advance whether we're going to blow the stack by calling the next function. And 2, it actually pre-allocates the stack every time it calls a function. And surprisingly, it actually it does one allocation to get everything. It needs what's called a frame object internally that represents the call. the nested call on the stack. And that frame object at the end has space for all the local variables and parameters followed by the entire stack in a variable amusingly called f_locals plus. I think this is the last slide on all of these fields, thank goodness. So annotations, gunk doesn't have any annotations, so this is empty, but this is where annotations will be stored. You remember Python 3 has that colon. There's a type annotations for parameters on a function, and it maps names to values. And it's bound at binding time, and it can have arbitrary values in it, so it's in the function object, not the code object. Closure, if gunk was a closure, this would be an object, but it's not, so it's none. Cell vars and free vars, if gunk was a nested function or contained a nested function, one of these might be empty, but they're not. Like I said, I'm not going to talk about cell vars and free vars, so I want to skip them. Now, as I mentioned before, modules in Python are callable objects. Consider that you just have a file and it contains code in it. Anytime you have the ability to run code in Python, you have a callable. And anytime you have a callable, you have a function and you have a code object. So I think it's really interesting that modules are themselves callables, which means that they're actually functions. Now what would a module look like if it was just a normal callable thing? Well, actually it would look pretty generic. A module doesn't take any parameters. It would just have all the code inside. It would use load name and store name. It would never use load fast and store fast. And I will tell you that every function in Python always returns something. If you don't explicitly return something, then you always return none. And so modules don't return anything interesting. There's no explicit return allowed in them. And so they always just return none. So you'll see this load const none return value. You'll see that a lot. Now, by the same token that modules are callables, classes are callables. This is a little bit more complicated. So first of all, classes actually do take a parameter. It's called dunderlocals. I'll talk about that in a minute. I kind of want to go from the bottom up here just because it gets from least to most complicated, like what the hell's going on. So again, at the bottom we have a return none because classes don't return anything either. They're not functions in the strictest sense. Above that we have this load name, store name, load const store name. Those are setting up two attributes of the class. That's dunder module and dunder qual name. And then above that we have this load fast 0 and store locals. Now what is that? Well, load fast 0, I again remind you that's going to be loading either a parameter or a local variable. In this case there's only one, and at 0 it's going to be the first parameter, which is local. So this is taking dunder locals and pushing it on the stack. Then it calls store locals. What is store locals? Store locals is one of those crazy super Pythonic things that's for the community, the interpreter. This is for a mechanism that was added in Python 3 called dunder prepare. It allows a meta class. So it used to be that a Python class, the class.dunderdict was always a dict. It was a real honest goodness dict. And there were people who said, I want to have a dict-like object there. I want to do exciting things. I don't know what the hell you would use this for, but it was important enough that it happened in Python 3. So there's this mechanism in a meta class. It's something called dunder prepare that allows you to substitute your own dict-like object for the real class dict when you create a class, and this is how it gets there. This dict-like object, whatever it is passed in to the class in the parameter called locals, and we store it into the class object there. Boy, that was complicated when I had to figure that out to write these slides. So, now that's what the function looks like to declare the class, but when you bind the class at runtime, there's also a little bit of code that you have to run. So this is what happens inside of the module, let's say, when you declare the class, and this is what turns the class into the attribute that you refer to. So the previous thing was at compile time, this is at class binding time. I really have to do this from the top down, but it's just weird. So first of all, load build class. This is another one of those super Pythonic, only relevant to the Python implementation opcodes, called load build class. What that does is it pushes onto the stack a reference to a callable object called build underscore class. It's dunder build underscore class. I'll get into that in a minute. But just for now, just imagine that lurking at the bottom of the stack. Above that, we push two things. The code object that represents the class, so the contents of the class if it was a function, that lives in that code object, and then the name of the class, and then we call this make function 0. Make function takes these two things, a code object and its name, and creates a function object. What does this 0 represent? The oparg is a bit field of three things combined together. It's the number of annotations, the number of defaults for positional parameters, and the number of defaults for keyword-only parameters. Since classes don't take any of the above, this number is just 0. The result of make function is a function object. It's a callable object. Then we call, we load another const onto there, the class name again. This is disobject. I don't remember whose output this is actually. It might be mine. But we load the name of the class onto the stack, and then we call function 2. Now what does call function do? Well, obviously that calls a callable object. The parameter, the oparg here, that's the number of positional parameters ORed with the number of keyword-only parameters. The way that works, it's kind of like the oparg. The keyword-only parameters are shifted left by 8, and the two numbers are ORed together. But the bottom 8 represents the number of positional parameters, and that's all you're ever going to see on my slide. So this means call function, and it takes 2 parameters. So this is going to pop the top 2 things off the stack. The first one is the name of the class. The second is the result of make function, which is our callable object. It represents the callable body of the class object. And then it's going to call a function, which is actually the third thing on the stack, which is what we got from load build class. So it's going to call this magical function called build class, which takes these 2 parameters, the callable object that represents the body of the class and the name of the class. And that does all the magical whizzy things to actually make the class happen. So if you want to create your own classes from bytecode, you have to have all this stuff. And you kind of have to have all the stuff on the previous slide too. Now, a little bit more interesting, I'm going to create a function by hand. I'm not going to use Python to do it. Well, I am going to use Python to do it, but I'm not going to use def. It only takes me 4 lines, but you're going to hate them. I have to import types, and then I create a code object with some of the most readable Python ever. And then I create a function object from that code object. I'm cleverly calling it add. You may be able to guess what it does. Yes, it takes 2 parameters, it adds them together, returns the result. So this prints 5. And there is no def add anywhere on the screen. Now, you don't understand what any of that means. So I'm going to do this again, but it's going to take me 3 slides, and I'm going to show you exactly what it means. So first, I need some more imports so that I can show you these symbolic constants. The rest of this slide, this is just for the bytecode. So op load fast, you can tell exactly what that means now. And then the 2 bytes after it, those are the oparg that are going to be ORed together. So this program is load fast 0, load fast 1, binary add, return value. Dis.opmap, that's a map of strings to opcodes. And then it's just a map, so I'm pulling get off of it. This is all of the parameters to the code object, and there are an awful lot of them. So arg count, 2, it takes 2 positional arguments. Keyword only arg count and local count, there are no locals, there are no keyword only arguments, so those are both 0. The total number of locals, again, I told you that's the number of positional only arguments plus the number of keyword only arguments plus star KWR, star args if we have one, we would add 1. Star KWRs if we had one, you'd add 1. And the number of local variables. So you would add that all together. I skipped the star args and star KWRs just because I was already running out of space. But the total number of locals actually is again going to be 2. Max stack depth, the deepest the stack will ever get in my add function is 2 because I push 2 things on the stack. Flags, this is that binary bit field flag thing that I mentioned a minute ago. This is the basic thing that you need for a modern Python function. So there are 3 fields here, CO optimized, CO new locals, and CO no free. What do those mean? I'm still not entirely sure. The best I can figure out is new locals means this function uses the fast locals array. Okay. Every function since 1992 has used the new locals array. I think even module objects that don't have it at all still specify CO new locals. Just everybody does. We probably should have gotten rid of the constant in Python 3 because everybody uses it. What does CO optimize mean? CO optimize also, optimized in this case doesn't mean the code is optimized, it means that the namespace is optimized. So it actually also kind of means this function uses the fast locals array. What it specifically means is local variables are stored in fast locals as opposed to slow locals using CO underscore name. So who does not get CO optimized? It's a very similar list. It's classes, it's modules, and it's eval. And back in the old days, when you could say import star inside of a function, doing that would turn off CO optimized because you could no longer use fast locals because you didn't know in advance what variables you were going to have. Onward. Oh, one more. CO underscore no free. That just means this function it has no free R's nor sterile vars. This saves Python some computation. It's just a little optimization flag. So, onward. The function doesn't have any constants, any names, globals, any free vars or cell vars, so those all get the empty tuple. It does have some local variables, A and B, specifically arguments, so I put those in var names. Theoretically, I typed this in as standard in, so I just put standard in for the file name. Name of the function is add, the first line number is 1. The LNO tab is empty because I didn't want the headache of calculating it. And we're off to the races. We create the code object, passing in all of those things in the right spots. And then the rest of the slide is exactly the same. We pass the code object and the globals dict. Again, functions carry their globals around with them, so you have to pass that in when you create it. And you get a callable object out of it. And you call it and you pass in 2 and 3 and you get 5. Now, this was still kind of painful. So that's why I wrote my own assembler and disassembler. I called it Maynard. I will remind you that Maynard was the keeper of the Holy Hand Grenade in Monty Python's The Holy Grail. The Holy Hand Grenade, of course, being the finest disassembler known to man or beast. So Maynard contains an assembler, a disassembler, all of the example code from this talk, and a very bad idea, which I'll talk about in a minute. So here is Maynard disassembling gunk, and I declare that this is a lot more readable this way. So you can tell A is a positional or keyword argument. It has a default of 1. B is a keyword-only argument. It has a default of 3. We have a star args variable. We called it args. We have two global variables, or two external globals that we might refer to, global and none. This is actually disassembling gunk, so it's printing out the none from the names array, but it doesn't actually ever get used. And then we have the constant value called const none up there. Then the body of gunk, I actually ran out of space, so I sort of clipped it, but we have load global print, load fast args, call function 1. That's calling a function with a single parameter, which is args, and the function we're calling is print. We pop top because we throw away the return code from call function because nobody ever cares what print returns. Load const none, we store it in C. That was that line C equals none. So you can actually tell everything that's going on inside of the function when you disassemble it with gunk. Now, eventually, I think the goal with Maynard is going to be to make it to doing recursive disassembly. So like if you disassemble a module, it would show you the class, and then it would disassemble a class in line, and if you had a method, it would disassemble the method in line, all of that being nested. It doesn't do that yet. It just prints out, oh, I have a code object here. But what if you want to look at the definition of a class? Well, you can do that with Maynard still. You just have to be a little creative. So what you do is you declare your class, and you do all the stuff you want to do inside of the class, and you take that and you put it inside of a function. Then you disassemble the function with Maynard, and then you look through the output, and you're going to see const index, then a number, and then the code object that represents the body of the class. Then just take this and pull it straight out of, see, I told you I was going to run out of time. You pull it straight out of the code object and disassemble that again, and that's going to give you the body of the class object. So here's the bad idea I mentioned a minute ago. I wanted to prove that you could write a language on top of Python without actually using def, without a language that ran on the Python bytecode interpreter that wasn't Python. So I wrote a fourth. It's called Perth. It ships with Maynard. It's a toy fourth on top of the Python VM. It's not useful for anything, but it does have integer, float, and string literals. It defines all of these Python words, including colon and semicolon, so you can define your own functions in Perth. It supports recursion, and that is just barely enough to allow you to run a Fibonacci generator, because I assert you don't have a real programming language until you can run Fibonacci. Now, I have, I think, 6 more slides. There's maybe 7. And we're going to bring everything all together. I'm going to show you a Python virtual machine written in Python. This is going to take a function, disassemble it, break it into bytecodes, and run the individual bytecodes. Now, gunk is really boring, so I'm not going to do gunk. I'm going to do a Fibonacci generator. So this is the function. I'm going to run this function in my own handwritten VM. And here we go. Def VM takes a callable object and takes star args. I declare all my local variables. Code is the code object. Constants is the constants table. Names is the name table. Program is the bytecode. and locals is the total number of local variables. Globals dict and built-ins dict, I have to pull the globals dict out of the function. I have to pull the built-ins dict out of the globals dict. And then I use those for load global. Instruction pointer is 0. Total locals array, that's going to be parameters plus the local variables. So I take all of the arguments and I just splat them in there, and then I create slots for all of the local variables, which I set to an uninitialized value I declared somewhere else. That's so that you can detect if you reference an uninitialized local variable. And then I create a stack, and the stack is empty. It's just a list because a stack works perfectly well. A list works perfectly well for a stack. Page 2. This is our big while loop. This is going to iterate forever. So we pull out the current instruction at the current instruction pointer, and we increment by 1. If we have an argument, I pull out the op-arg, I reassemble it, and I advance by 2 more. The rest of the entire function, all it's going to be is these if op double equals statements. All we're going to do for the rest of the function is handling individual opcodes. First one is op load const, and it's 1 line. If op equals load const, we look up op-arg in the constants array, and we add it to the top of the stack. Load fast. We look up op-arg in the locals array, and we add it to the top of the stack. Load global. We take the op-arg, we look it up in the names array, and that's the name we're looking up. If it's in the globals dict, we add that to the stack. Else, we add that from the built-ins to the stack. I don't handle an error because it's only handling fib. Next page. If it's binary add, I pop the top 2 things off the stack, add them together, push the result. Same thing with binary subtract, except I use a minus sign. Pop jump if false. This is how you do if statements. If the top value on the stack is false, then the op-arg is going to be the new instruction pointer offset. So that's how we jump. We change the instruction pointer to be this new value. Boom, we're off to the races. 2 more slides, I think. Compare op. We pop the top 2 things off the stack. Compare op, this is the general purpose mechanism used for comparison in Python. That's for less than and greater than, all of those, what's called rich comparisons. So the way that works is you pop the top 2 things off the stack, and the op-arg represents which operation you're doing. So pi_lt, I had to get that out of inspect, I think. If it's lt, then it's less than. I return v is less than w. If it's less than or equal to, I do v less than or equal to w, else I throw an exception. Regardless, if I succeed, then I just push that value to the top of the stack. Call function, this is the last slide. I really should have shown you the disassembly for fib, but I forgot. Call function, so first the op, again, that's the number of keyword only parameters and the number of positional only parameters. I don't handle keyword only parameters, so if the number is greater than 255, I throw an assertion and I fail. But now op-arg represents the number of positional only parameters, so I pop them off the stack and stick them into an array. That becomes args. I pop the callable object off the stack, and I call VM recursively, splatting in the arguments. The return value from VM is going to be the computed value of the function I just called, and I just push that onto the top of the stack. And finally, return value, opcode. I assert that the stack has depth 1 because it would be untidy if you had leftover other gunk on the stack, although Python doesn't actually do this. Anyway, I just take the top value off the stack, which is 0, and I return it. Oh, I had all of those. Well, I forgot. Anyway, this really, really works. If I drive it from Python, the Fibonacci number 0 through 9, I call the real function, I call my VM and pass in the same fib function, it produces identical results. It really, really works. So, if you ever choose to experiment with opcodes yourself, writing your own functions and assembling them, expect to see this a lot. The Python interpreter is not particularly resistant to malformed bytecode, so expect it to crash. And when it crashes, it'll give you no hints. You'll have to sit there and think, now what did I do wrong? I've asked other core developers if we could maybe make it a little stronger, maybe check some things before we do them. They're like, it's bytecode. If you're doing bytecode, then you should expect to crash. It's on you. So finally, some resources in case you want to read some more about it. Oops, I have one of those that didn't fade in. This, inspect, and dunder future, you need to look in all of those modules to get all of the constants you would need in order to deal with bytecodes. Dunder future has some that are specific to future importable things. Maynard is my disassembler. It's up on Bitbucket. It's up on PyPy. I think the Bitbucket version is a little fresher. If you want to read C, the implementation of the Python virtual machine, the bytecodes are all implemented in this file, python/c-eval.c in the Python trunk. And finally, if you want to read another implementation of a Python virtual machine in Python, Ned Batchelder has been writing a very nice one called byterun that really does everything, including local variables and cell variables and free variables. Okay, I'm done.
Larry, thank you very much.
Oh.
Larry. Larry, thank you very much. Do you have for those bytecodes something like how many cycles do they take? Like we had for real assembler? It's not cycles, I know, but...
Yeah. No, the answer to that would be no, you really can't tell. Some of them can be very slow indeed. Like star I think is a single bytecode, and that turns into a very complicated process. So there can be loops inside of bytecodes. There's really no established thing. You can just sort of think conceptually like addition is going to be fast. Actually, you can't even think that because it's been called dunder add, and dunder add could do anything inside. So there's really no telling.
So thank you, that was impressive. I guess that's the only word I have for that. I was wondering, if I define all this myself and then I'll set the max depth of my stack not deep enough, I'll get a...
You will crash. And that's actually, this is a good point. So you have to calculate the stack. So the first thing you could do is just add 1,000 and see if you run now. What I will tell you is that the hardest thing actually in writing Maynard was calculating the stack depth, because that's not information that's published anywhere in Python. It's internal only. There's a function in C called calculate stack depth or something like that. And I literally had to take that, copy it out of the Python source code, put it into a little function, into a little program, and then drive it from Python to produce a table. And Maynard is based off of that table. And the other thing that I'll tell you that's even more complicated is that the stack depth used by any instruction might change depending on the oparg. For instance, the obvious one is call function. Call function, the oparg reflects how many arguments you have. And so you can calculate how deep the stack is, but you have to know the oparg first. So if you want to play with assembly, again, I would absolutely recommend that you look at Maynard and you can pull out the stack depth calculator. I actually asked this week if I could just add that to Python, like we could stick it in the dis module somewhere, a function that says, for this op, with this oparg, what's the stack depth change? And people were like, yeah, it's fine. So it'll probably go into 3.4. Yes. Oh, it went to sleep. I talked too long.
Hello. Oh, okay. So why the whole shifting thing with the arguments of opcodes?
Because Guido wanted it that way. It has to be one way or the other, and arguably this is what's called network byte order. You need to store them somehow, and network byte order is a pretty obvious order that everybody knows, and so he just did network byte order. I imagine that was his thinking. You'd really have to go back to 1992 and ask Guido. I have stunned you all into silence. Okay, thank you very much.